today. You will have to suffer me for two lectures in a row. I don't know how you're going to survive. Or how I do. Alright, okay, so the plan is this. The first lecture I want to devote to derivation, relatively weak and sketchy, but hopefully still clear, of the kinetic equation and discussion of what is kinetic equation, what is it written on, and what are sort of conceptual things around it. And the second lecture I want to devote to the classical limit and show you what is a classical limit of the Keldysh technique, which was known to smart people much before Keldysh actually, and much before Schwinger even. So, but today we, of course, understand that it's all one and the same thing, so I want to show you the connections between them. Right? Yeah.
Are we covering any noise related to...
Yeah, this classical story will be entirely about the noise. Right? So if you're waiting for noise, then wait for a second lecture. All right. So then today, now we're doing kinetic equation. So remember what we got so far is that we have an action, and this action is written in terms of pair of fields, which we call classical and quantum. And this action pretty generically has a quadratic part, that's what you would expect, classical quantum. Quantum. And then nonlinear part, I'll write it in a moment, so let me go back to the classical part, to the quadratic part. So again, you expect here 0, and this is wholly because of normalization, and then you expect something advanced classical operator sitting here, the same operator but in retarded, basically transpose matrix, if you think about it as a matrix and time representation. Retarded operator, and then there is something which we call a Keldysh part sitting here. Now the interaction depends, of course, what interaction you take. What we considered was phi to the 4, phi to the 4 interaction, and once you write it in terms of this classical and quantum, then what you got is things like two diagonals, one like this, and one like this. Where quantum field, dashed line is a quantum field, and full lines are classical field. Okay? So that's what we got so far. And then what we discussed, that if you look for the saddle point equations, then you look for ds for d phi quantum equal to 0, ds d phi classical also equal to 0. Now this one, we argue that one of the solutions, not necessarily all of the solutions, but one of the solutions is phi quantum equal to 0. And then this, the first one, give you grossly biased. Or if you deal with another example, that maybe any other classical equation which underlines your quantum field. Okay? And again, there is a very interesting discussion of whether there are other saddle points, and if there are, what to do with them, what they correspond to. So this oscillatory level statistics is one of the examples of saddle point where essentially phi quantum is not equal to 0. But I'm not going to. Okay, so that was about saddle points. So now we want to include fluctuations. Right? I'll do it using perturbation theory, although the result is not necessarily perturbed. you'll see what I mean. I will formally sum entire perturbation theory, but then I of course resort to some approximations better. Okay, so now here we got a choice how serious we are about Bose condensation. Because if we are serious about Bose condensation, then we first have to solve Gross-Kitaevsky equation, find the condensate. In a uniform system, it's just a constant. In non-uniform system, if you have a trap, and trap potential is sitting somewhere here in your operator, so it will immediately transform into here because basically this Gross-Kitaevsky equation is retarded all the way to everything on point plus non-linearity. So then your condensate has some shape, and then you have to develop perturbation theory around this shape, and that would be theory which takes condensate and quasi-particles, valuable quasi-particles if you wish, on top of this condensate. Yes, please.
Is there an intuitive way to see that the trap only appears in the advanced and the retarded parts of the Green's function and not in the Keldysh part?
Yes, definitely. You start from your Keldysh contour, and you write it dt phi dt minus the plus grad swell to m plus trap. Something like this, and then you go to phi plus, phi minus, and do linear transformation. Believe me, that's not with that. Good question. Again, as I sort of alluded to, this guy is about fluctuations. Noise, if you wish, as Luca wants. So trap is not about noise. It's stationary. Now, that will not be able to do here. It's not conceptually difficult, but it will take me too much time. Although it's written in my book, or in our books. Anyway, what I will take an easy way out. I will assume, if you wish, that temperature is above Tc, so there is no condensate, and then I will do perturbation theory on top of zero. So I'm sitting in a situation where solution of this classical seven-point equation is also trivial. Right? But you should understand that it's by any means not a generic sort of most generic case. It's just I'm taking easy way out, doing whatever so simple. Okay. Yes?
Sorry, another stupid question. Where did
No, I
temperature
understood the
enter?
answers.
Where did temperature enter into this formulation? Is it in the time integral?
Very good. Very good. Where the temperature enters. Can we postpone this question? It's a very good question, and it's not shallow. Not stupid at all. Other questions? All right. So I'm doing the most primitive thing, which I think somebody suggested yesterday, to start even with, to do perturbation theory on top of zero. Okay, good. So now the first thing to convince yourself is actually whether you understand that z equal to 1. And sort of keep insisting that it's a good thing to understand it at each and every stage of your calculation. Now we sort of convinced ourselves that as long as we don't have interruptions and we take only this, then that was the case. Right? So now I'm adding interaction and I'm claiming that that's still the case. Right? So how do I check it? So I will write it as d phi, classical quantum. I will take two quadratic parts of the Hamiltonian here, right? And I will mentally expand this interaction part, 1 plus I s interaction minus 1 half s interaction. That. Right? And so we know that if I take this, then that's already true. Right? So then what I'm essentially claiming is that if I take this term, it is 0, and this term is 0, and any other term in this perturbation theory is trivially 0. Okay? So I'm basically claiming that any power of S interaction averaged with the Gaussian weight should be 0.
Is it not possible the series could sum up to 0, but the terms could be non-zero?
Yeah, of course, there are all kind of fancy scenarios, but fortunately here we are in a trivial situation. Each diagram, not even each term in this series, but each diagram separately is a little bit of this situation. Almost. Anyway, so that's what we want to see, right? So how does it come about? I take these guys, expand it, and then I contract them according to weak theory, right? Okay, so let's look at the first term, S to the power of 1 interaction. Then I have these two terms. Now remember what are my rules of the game. I have three types of the green functions. I have this one, which is retarded, this one, which is called advanced, and then I have this one, and I don't have anything like this. That is a manifestation of this zero. Right? Okay, so I take this. I have two of those. So the first one will give me something like and the second one would give me okay. Now this one is 0 because there is nothing like this. Okay. This one is not a priori 0 because there are such green functions. But notice what happened. I have a retarded green function, and I calculated it in coinciding times. Okay. So I got G retarded and T times G Kelvin. And then there is actually complex conjugated diagrams with inverted, reversed directions of arrows. If I took two of them, then again one of them will be trivially 0, and another one will give me G advanced at GT. And if you remember previous class, I insisted that this one is a wholly 0, and you can track it really down to the discrete representation and see that it is 0. Okay? So the first order is 0 because of that. Now we'll go to the second order, and I'm not going to go past the second order, of course, because you will see all the sort of building blocks of the construction. So now I have to take two vertices. Two vertices, right? Now clearly that if I take two vertices like this, then unavoidably at least one of my lines will want to be fully dashed, and nothing will happen. So I have to worry about two vertices like this, or maybe one vertex like this and another like this. Okay, so let me see if I can do it. So let's probably take two of both. So we'll have and now I have to contract everything, so the most interesting term which I will obtain is this. Again, I of course want to avoid contracting dash to dash because that is trivially 0. So I want to contract dash with a full line. This dash I also contract with a full line, and then the remaining full lines I contract between myself. Right? So that, and then I have other diagrams, but that's conceptually important. And I claim it is 0. So anybody can guess is 0 without any.
So what is the relation between GA and GR if we swap the time? What is the relation?
Yeah.
I mean, that must be the
Right. So I have two time points here, t and c prime. So I have one of retarded in function, so g retarded c prime times g advanced t prime, and then whatever, g kel dash square. But our main hero is this. So we understand that this is a lower triangular matrix, this is an upper triangular matrix. If you wish, this has t minus. This has t prime minus t. So they are incompatible. Right? So it is tempting to call it 0. Now here you actually have to be a little bit more careful, because as I said, that's not true at the diagonal. And if t literally equal to t prime, then this guy is not 0. Right? But we shouldn't worry about it. Why? Because if you go back to your discrete notations, you have two integrations here, dt prime. Back to the discrete notation, it will be two summations, j and j prime. Right? And the only non-zero terms here are those which are sitting right at the diagonal. Right? So this is a set of measure 0 once your n goes to infinity, number of discretization points. Then whatever left of the diagonal dies away. Okay? And this is why I'm saying that although there is some problem with the diagonal, it never sort of gives you real trouble. It is a measure 0 set. Okay? Good. So there are two mechanisms of these cancellations. One of them is because you simply get retarded and advanced green functions at coinciding time, or you got retarded and advanced which are incompatible causality-wise with each other. Right? And all cancellations in this theory always have one of these two shapes, either one or another. So you can show that no matter how far away you go in this perturbation term series, all diagrams will have either this construction or that construction. Yes?
Sorry, could you please remind me why, like in your original action, that terms like 2 classical and 2 quantum cannot exist?
2 quantum can.
The interaction.
No, I mean interaction term, the G term, 5-4.
Oh, very good. Okay, so there are two ways of arguing about it. One is to say that because of time reversal invariance, I must have even terms in quantum field taken back, or the terms in quantum field, because if you reverse time, you interchange upper contour with the lower contour, that's phi quantum goes to minus phi quantum, and the invariance requires that it's an odd function. Okay? Or just simply algebraically, you start from base, you write it as phi plus scalar minus phi minus, and then this is your classical plus quantum, and this is your classical minus quantum. And you do 2 minutes of algebra and you convince yourself that that's the case. I'll give you in a moment example phi cubed, and then you will see it's a slightly different, same concept. More questions? Good. Okay. So we are successful in calculating what? Time after time. Still almost useless manipulation. So to make it useful, you want to calculate again correlation function, namely dressed green function. Capital G, ET prime, and RR prime. So you want to average phi alpha TR, phi beta T prime R prime with the action S naught as interaction, where again alpha and beta are my Keldysh indices. Okay. So, and again, we want to do perturbation theory, so I take this and I extend it. Instead of that, I get 1 plus IS interaction. Okay, and I'm calculating green function. So the first term is my bare green function, which I will call G naught. And then I'm starting having perturbative corrections to the green function. Right? So let's say I take the first order problem. So my green function is bare green function. And again, it's matrix. It's alpha beta. So my drawing is a little bit oversimplified because the matrix contains all three of them, but I'm just trying to show you very schematic structure. Remind you know it. So then the first term will be something like this, and then the second term will be something like this. Now in principle, I could also have terms like this. Disconnected diagrams, right? But what we just proved, essentially, this exercise was about proving that there are no disconnected diagrams, because disconnected diagrams is about taking separate average of this and separate average of that. Right? So essentially, this exercise, which is still in the middle of the blackboard, is about proving that in this theory there are no disconnected diagrams, which I already claimed in the very first class, that that's the same statement as having normalization equal to 1. Okay, good. So we should not worry about this. And then, as always, we can rearrange this series in a Dyson way, so that the full green function plus then you claim this is where sigma is a sum of all irreducible connected diagrams. I shouldn't go deeper in what the Dyson relation is. Right? So it's, from conceptual point of view, it's completely standard Dyson. But the devil is, of course, into details because.
So, this being a bosonic theory, will the symmetry factors create any problems while finding certain?
What way should
So in fermions, it's very easy to see that it's just an expansion of 1 by 1 minus x. So you have 1 plus x squared plus x cubed and so on and so
What
on.
is that? Oh, you
I mean that the Feynman diagrams could have some.
you mean when you sum at 1 minus sigma versus 1 plus sigma, something like that?
No, so when you expand the exponential, you have a 1 over n factorial for a
Yes.
diagram with n factors of the
Yes.
interaction.
Right.
So in fermions, that when you count the number of diagrams, possibilities you get like that, it comes out to
The Feynman diagrammatic technique, which is about, telling you that there is no devil in the factorial factors, equally well is applicable for bosons and for Fermions. There's nothing specific about Fermions. Yeah, sure. I mean, from a electromagnetic field lines in standard Feynman technique are bosonic lines.
Right.
You can do self-energy for your electromagnetic field. RPA approximation, what we call it. So this is bosonic perturbation theory.
Right.
So, yeah, but that is certainly okay. What requires discussion is the fact that everything is matrix here, so that my sigma is also a matrix, right? And all these multiplications should be understood as convolutions, or matrix multiplication, both in time space and in Keldysh flat flavor space. Okay? But that's okay. If you have any intermediate index, be it spin or be it replica or be it whatever, you know that diagrammatic theory is arranged in a way that you always have just intermediate indexes summed up. So it's a matrix. Okay, so we understand that this sigma is a 2x2 matrix, and it also matrix in a time space, of course, but I'm now focusing on this flavor Keldysh space. And I claim that it also has a very definite causality properties. Okay? So, can you guess what they are? Hmm? This is 2x2 matrix in this Keldysh space. Okay, and what we know about their propagator is that it has very definite features. Here is 0, here is upper triangular part, lower triangular part, anti-Hermitian matrix, and here.
Same structure?
So same structure.
Right. So it is the same structure because it is a renormalization of this Baire propagator. Right? So if this is of any value, then it better be preserved. Right? So at the moment I just claim that this thing is the same structure. Again, in the same sense that this, in time space, this is an upper triangular matrix, this is a lower triangular matrix. This is anti-Hermitian. Yes?
Is this something like a word identity type of thing?
No, or at least I don't know to formulate it as a word. And I don't know what's the underlying kind of symbol. And port identities are always it's manifestation of causality. Wherever you can reformulate causality as a symmetry and then corresponding port identity, I don't know what to do. Maybe it's possible. Okay? Now, instead of trying to prove it in any generality, I will simply give you in a moment a sort of simplest but non-trivial example where you will see why this thing holds, right? And then you will sort of see that order by order it must be true. Okay? But for a while, let's take this thing for granted and let's try to proceed assuming that I'm not cheating. Okay? It's better. So what we're discussing is essentially Dyson equation. Which says that G is equal to G naught plus G naught sigma G. Where this circle simply reminds you that this is matrix multiplication and time convolution in the middle points, right? So now let's see how I want to proceed. So now you can take this to the left-hand side and then you can write it as and multiply by G naught minus 1. So in a standard way, you can write it like this. Now this is an inverse matrix, so let me now expand it and write this Keldysh structure explicitly. So this one is my classical equation of motion, so it has this structure G advanced minus 1 minus sigma advanced G retarded minus 1 retarded. And this is a sigma Keldysh. Why? Because remember that in my Baire theory, this stuff was just pure regularization. It was sitting here to remind you how to invert the matrix. It was 2I0 times my distribution function. Now, since I'm claiming that I'm going to have something finite in this block, I don't have to worry and keep any more the regularization. Okay, and this is acting on G. Now about G, I understand that it also has the structure which it's supposed to have. So check here, this should be once and 0. Don't equal to 1. Okay, so now what you see is that your equation sort of nicely splits into pieces. Namely, if I take the first line multiplied by first row and declare that this is 1, it's all about advanced component. And so I will take G advanced minus 1 minus advanced. So this was G naught. Sort of careless about soil. Is equal to 1, and of course if I take what the second line and multiply it by the second row, I'm getting the same thing but for the retarded. It's supposed to be because they're just mutually Hermitian conjugated, so that's pretty much one and the same equation.
You mean minus sigma k? You mean minus sigma k?
What?
Bottom right on your bottom equation.
I take the second line, multiply
That
by
sigma
the
k you just pointed to. That sigma k you just pointed to should be minus sigma k, shouldn't it?
minus. Yes, thank you. Right, so there is a closed equation on retarded and advanced green functions. So if you recall what this is an operator which is IDT plus Gaussian square to them, maybe trap potential, whatever it is, and then sigma, which is actually not necessarily a local object in time and space. CT prime, R prime, data function T minus T prime. This is what this one actually means. Delta R minus T prime. And if you have some approximation, some idea what is the sigma advanced, sort of looking, calculating some diagram, you presumably can go ahead and solve. In particular, if I don't have trap potential and everything is sort of stationary and translation invariant, then I can go to the Fourier space and then my life becomes relatively easy. Or I can write epsilon p minus epsilon k G advanced is equal to 1. So G advanced of epsilon p is going to be 1 divided epsilon minus epsilon k minus sigma advanced of And of course, the sigma advanced of epsilon t should be such that all poles are sitting only in the upper half plane of epsilon.
Is there a difference between GA to the minus 1 and GR to the minus 1 in the continuum limits?
To the zero approximation, no, because all the difference is just this plus minus and zero. Right? Now, once you have this sigma, which is finite, it will automatically do this thing for you, because it has imaginary part in general, and this imaginary part has a proper sign. Okay? Now, if you don't have any sigma, then you should be a little bit okay. Since we already have it, I'm completely at liberty to get it. All right, so this guy is conceptually not any different from what you're familiar from the usual equilibrium perturbation theory, so I'm not going to spend more time on this. Right? But there is one additional component which we obtain if I take this second line and multiply it here. Right? And that's a non-trivial part of the story. So first of all, it should be zero on the right-hand side because I'm taking taking something like G naught R minus 1 minus sigma R acting on G Keldysh minus sigma K G advanced is equal to 0. They are not matrices in a flavor sense, but they're still time convolutions, of course. Okay, so now you have to recall that you can always parameterize anti-Hermitian matrix GK in the following way. The retarded and advanced are mutually Hermitian conjugated. So that's, there is no assumptions here as far as I understand, it's just parameterization. Where F is in principle non-local object, dependent precise. We'll discuss in a sec how to make it a little bit more physically transparent, but for now it's just a matrix. So now you substitute this into here. And then you, what? Let's see.
Alex,
Yes,
is F symmetric under exchange of T and D prime?
yes, F is Hermitian. Okay.
Can you say something about sigma k based on this parameterization?
Yes, sigma k is anti-Hermitian
So you
thing
can
because it's sitting here. You see that what was here was F with I side. So whatever it is, this should better be anti-Hermitian construction. All right, so then with some completely trivial algebraic manipulation, we got that F G naught advanced minus 1 minus GR naught minus 1 F is equal to sigma K minus sigma So finally, I can recall what are my bare green functions and what were just this classical operator. So what you got is now with all signs taken care of, I dt minus 1/2m gradient square minus trap potential, if you wish, CMR, commutator with F, this is these two terms, is equal to this CA minus sigma with F minus F sigma dot. Okay. So what I'm going to show you that, yeah, so this is a commutator. You see this operator on that. You should look at it as a matrix in a time space. So you multiply this matrix on that and minus vice versa.
I lost the track of this term, sigma r, grf. In the second line,
Good question. Yes, right. So when I say the trivial algebraic manipulation, I slightly cheated here because while doing this algebraic manipulation, you should use this. Understand it? If I act with this on. Yeah, so there is one line of algebra in between, I'm skipping, but believe me, it's a trivial one. Okay, so this thing is going to be a kinetic equation with its left-hand side pretty much representing kinetic term, the flow, Liouvillean flow, and the right-hand side representing, by and large, collision integral. Okay, it's a little bit misleading because this part you will see slightly renormalize the Liouvillean part, but that's sort of peculiarity. So this is pretty much collision integral. I think Anton called it SP. I will call it I. But they're dependent sort of notations. Now the important thing is that in general you may know that collision integral has two parts. One is in part and one is out. Is it something everybody appreciates? You look for the probability for the given state to be occupied, and there are two parts of it. Particles may leave this state, this is out, or they can come from all other states to the state you're looking at. Right? So pretty much what you will find that this part is an in part of the collision integral. This part is an out part of the collision. Remind me if I forget to sort of reiterate it once we have an explicit example. Yeah.
is that a plus in front of del square by 2n? It's basically I del tau minus h, right? The Liouvillean operator. The first operator, which is I del tau minus
But, you know, by definition, all my signs are correct with probability 1/2. Which is pretty high probability. All right. Now, yes, please.
So in the usual equilibrium perturbation theory, you might have this situation in which the initial structure of the non-interacting Hamiltonian sometimes is not the same structure of the self-energy
Yes.
by some non-conservative effects, right?
Yes.
So is there a possibility here of some self-consistent solutions also?
Yes. That's precisely what I sort of alluded to in passing, that this part is actually not only out part of the collision integral, it also contains renormalization of this one, which actually better be the case because you see that here. The Liouvillean flow is easily normalized. That's about the Liouvillean flow. Yeah, you're precisely right, and it is still in this equation. We haven't missed it yet. We can if we will be not very careful on the next step, but
But I also mean something even more dramatic. Say this structure of this retarded part being essentially the transpose of the advance. Would that ever break down or?
no, causality is never going to be violated, as far as I understand, right? So whatever drastic your denormalizations are, we are not going to violate causality. And this structure is solely about causality. Okay. But you're right that this operator, if you wish, may be actually drastically modified. Not everyday situation, but it's possible. And this normalization is actually sitting here. So. Yes?
If the system has a magnetic field, then if I'm doing some gauge transformation, then is this structure preserved?
Well, yes, gauge invariance is a good question, because actually what we're calculating is green function. Is not a gauge invariant object. Right? So I don't want to go into it. We can talk privately, but it will leave me. It's an hour. So yeah, it's something to worry about, but not here. More questions? Okay, good. So then what remains to do is first I need to show you that I'm not cheating, and that's indeed the case. And then I need to show you how to make good out of this monster. Okay, so two kind of pieces which I want to achieve in the next, whatever, 45 minutes. So maybe let's first take an example and convince ourselves that this structure works, and then go back to here and do something like that. Okay. Now, we could do it for this example with phi to the 4, but there are too many lines. So I want to simplify my life, and I want to take an example phi to the 3. Okay. For that, of course, you need to work with the real fields, not with the complex field. You can have phi to the 3 for the complex field. But it's pretty much the same. You probably will allow me to assume that real fields are not that much different complex fields. Of course, actually, the operators should be second order in time derivatives, not the first order. But okay. All right. So I'm taking now phi to the 3 interruption. So see what notations I'm going to follow. Gamma by gamma. So I will have gamma phi to the 3, and phi is now real. Sorry for and it will produce me things like this. It will give me, after I split it onto forward, backward, classical quantum, it will give me 2 vertices. This one actually comes with gamma, and this one comes with gamma over 3. If you work hard at it, it's not essential. Okay. Again, you could anticipate it from the very beginning, because we know that it should be odd in quantum fields. So the quantum field can be either in the first power or in the third power, and that's of course all what you can get from this. Okay. Slightly different coefficient. Forget about it. All right. So now we want to calculate free energy. Take it back, self-energy. And this self-energy has, in the second order at gamma, I'm not going to go any further than second order. So let's first calculate classical component of self-energy, which we know should be what?
0.
0. So I'm doing a very intelligent exercise and calculating what I'm claiming should be 0. But again, it's instructive to see why it is actually 0. So this is a thing which should have 2 classical legs. Okay. So I should play with these 2 vertices having one of those legs to be classical. And that immediately put this vertex out of the game because it had no classical legs. So the only possibility is to take 2 vertices like this. And then I have things like this and things like this. And again, you understand that I cannot try to pair this with that because dashed line is 0. So the only possibility to play with is this. Right? And for miracle, that's again the same construction, G retarded of T prime times G advanced T prime. And very incompatible causality wise. So this with 0 is indeed 0. Good. At least I'm not cheating about that thing. Okay, now let's go next. So I want to calculate classical quantum, which I claim to be work advanced quantum. So that means that this leg should be full, but this leg should be dashed. Okay? So that means that for this vertex, I don't have any choice but taking this guy. So again, have this. Now for this vertex, you see that if I will try to take this fellow, I will necessarily have to contract dashed line with a dashed line, and that's a bad idea. So again, the second fellow must be one of those. But now the external leg is dashed, so the remaining 2 legs are full. So now I do contraction this way. Okay. So this is my G Cavendish, and this is my G advanced. Right? So this is self-energy. So what we find is that self-energy of T and T prime is nothing else than G advanced T prime times algebraically times, not matrix multiplication, just algebraic multiplication of G Cavendish T prime. Okay? And we know that this thing contains theta function. So it's an upper triangular matrix in a time space. So we immediately conclude that this guy is also containing theta function. So it's upper triangular matrix, and therefore my designation of it to be retarded is advanced, so it's true. Right? So same goes for retarded, of course. Your diagram is going to be just opposite. And the result will be G retarded of T prime times G Cavendish of T prime. And again, you immediately see that it contains theta function, T minus T prime. So this object is indeed retarded. Now, for the fun of it, let's discuss what the Cavendish one is, because I will need the expression to discuss collision integral. Okay, so for the Cavendish one, we want to calculate sigma quantum, and by definition call it sigma Cavendish. So I will need to have 2 dashed legs. Okay. And now I have different possibilities. So I can again take two of those. So then I will have diagonal like this. But I could also take one of those and one of those. And I can have an opposite situation like that. So what I got for some energy is therefore G Keldysh square, again in the same sense as here. This one is G advanced square and the is G hardened square, and the lowest one is G advanced square.
This 5 cube is just for illustration, right? Because the theory is not good, right? It's not stable.
Yes, very good. So phi cube is, of course, should be understood with care, because if you think the potential is always like, I don't know, at best like this, right? So what I'm doing, I'm sort of discussing small fluctuation. If you think about it as a big membrane, let's say, right? And my real variable is a transverse coordinate of the membrane. And I just describe non-equilibrium fluctuations of this membrane. So I sort of, at the moment, not thinking what if it activates over this barrier and disintegrates in some sense. I'm simply worried about small fluctuations around this medium. Yes, you're right. It should be taken with care. It's just an illustration of how the technique works rather than honest to goodness physics.
How do you show this is anti-Hermitian?
How do you show that this is anti-Hermitian? I'm probably forgetting some i's along the way, right? Yeah, let me see. Yes, there is another I, which I'm forgetting. And then it's probably easy to see that it is. Yeah. The I is there or not there of probability. Now there is one useful trick to play with this. You say that this is G Keldysh square plus G retarded minus G advanced square. And they claim that this is an identical manipulation. Why is that? Very good, because I shouldn't worry about the cross products. They're of that sort. And we agree to throw them away. Okay, so that sort of shows you, and you can easily extend this to any other higher order of the perturbation theory, and you will order by order see that this is zero no matter what. This one always contains advanced function between initial and final point. And this is some. Right? So I'm not claiming that this is a mathematical proof, but I'm just trying to show you that if you do it order by order, you will be recovering this structure order by order. Okay. Yes?
Maybe this is unimportant, but earlier you justified tossing out these G-retarded G-advanced products because you integrated the constant over a measured rate set. Here it's in the self-energy, so it's not yet being integrated over. Is it necessarily legit to toss it?
Yeah, that's a good question. But again, you mentally should think that this self-energy is nothing else but sitting in your action, right? Renormalizing your action. And it's a convolution with conjugated vector and vector here, so it's always in the integrals. It never by itself. Good question. Yes.
So one feature of the Matsubara technique is that if you just do second order perturbation theory, you can turn that into a one loop RG and you sum up a much larger class of diagrams. does the same feature hold here with the additional structure? I mean, can you turn this into a one-loop Keldysh RG and?
No, I mean, you certainly summing by infinite series by writing Dyson equation, right? It's not that you just do second order perturbation theory. Right? Whether you can make it RG or not, that's a very sort of deep philosophical question. What is RG? Because in principle, since you have this additional 2x2 structure, you have a priori more constants in the field. For example, here I'm claiming here that this is gamma and this is gamma over 3, right? Suppose you're doing normalization. Should this relation remain between them, or should I sort of let them loose and renormalize each one separately? And there are a number of constants proliferate. So how to do the RG in Keldysh? And before that, what does it mean? Where do you expect scale invariance? Why to do RG at all? Right. Because in a generic non-equilibrium state, you do not expect any.
Right.
So RG is. But there are situations where you do expect. For example, there are genuinely non-equilibrium second order phase transitions like KTZ equation or whatever, right? And where your RG is appropriate. And how to do them is a very good question, and I will not discuss it here. But it's written in my book. No, sorry, in case I can't do it.
You can ask about you can sit in a phase, let's say a superfluid phase, and ask about relevance.
Yes, you can ask about relevance and the relevance.
Scaling comes from
yes.
Going to the Gaussian fixed point.
You can. Even that is sort of not quite trivial question, because if you're sitting in a classical limit and you're sort of describing classical phase transition, counting relevance and relevance of these vertices goes one way. If you discuss quantum phase transition, then the counting of relevance and the relevance will go completely different. So it's tricky even in an equilibrium setting.
Right.
And nothing too complicated, but certainly beyond what I can do here.
Right, but you're just saying there's a temperature, so temperature is relevant.
Right. But how it translates with scaling of classical component versus quantum component. Essentially, in finite temperature setup, quantum components are always less relevant than classical, and in the context of quantum phase transition, they have the same scaling dimension. All right, good. So that was the first part of the story I motivated with. Now the second part is we need to make sense out of this beast. And the best way of doing it, I know, is to use Wigner transformation. Okay, so I need to remind you the Wigner transformation, because so far what we are doing is equation for two-point correlation function, which has 2 times. And I don't know about you, but I have zero intuition about two-point correlation functions. Okay? So therefore, it's a good idea to simplify our life a little bit. And the good tool for this is a Wigner transformation. Namely, if you see a 2-point object, you introduce center of mass variable, and you introduce Fourier transform with respect to the difference. Now I'm sure Tolia Polkovnikov will use it extensively, so I think it's even in the title of his lectures. So let me just briefly remind you. So if you have a 2-point object, you want to introduce t as t plus t prime over 2, and you want to introduce, I don't know, delta t is t minus t prime. So you go to a t and delta t, and then you do a Fourier transform with respect to delta t, so you go to a t, it's not temperature, it's center of mass, t prime, t double prime. essentially function of energy. If we would be in a stationary situation where my correlation function depends only on t minus t prime, then of course I would do Fourier transfer and go to A of epsilon, right? That first thing which we are told to do. But I say that if my time translational invariance is violated somehow, so there is no this minus here, I still can go to the function, which is a function of epsilon, but it also depends on the center of mass time, where exactly I do this Fourier transfer. Okay? That, of course, useful procedure only in the case where there is some hidden, or not very hidden, separation of time scales. There is some fast oscillations on a scale, I don't know, epsilon Fermi. Okay? And then there are some slower variation on a scale of disorder, whatever, scattering length. Okay? Scattering time. If that is not the case, then formally you of course can do this manipulation, but it's not going to be really useful. Now, why is it a good idea? Because now we, instead of writing matrix convolutions like we're reading here, we can go to algebraic products. Okay? And the only important notion is the following. Yes. So if I have matrix C, which is a matrix convolution of A and B. So that's essentially means it's C of T and T prime, A of T, T double prime, B of T double prime, T prime, and integration dt double prime. Right? So if I have this convolution, now I can do a Wigner transform of A and B and ask myself, can I express Wigner transform of C if I know Wigner transform of these two guys? Right? And the answer is this, that C of epsilon and T, let me change T and epsilon, is the following thing. It's A T and epsilon, exponent of I over 2 d T d epsilon minus d epsilon dt d T epsilon. So instead of, so this arrows indicate where this derivative goes, to the left or to the right. And the meaning of this exponent is simply that if you expand it, you got a differential operator. So we traded this integral into the infinite sum of higher and higher and higher derivatives. And that's in principle, in general, that's called Maillard expansion, I believe, with expanding this exponent. So it's not very useful unless you can restrict yourself to the lowest order, or two lowest orders. Okay? And the assumption which goes behind this is precisely this time scale separation. So this product of these two derivatives should be in some sense small. You see it's a dimensionless object. So variation with respect to this should be much slower than variation with respect to this.
With a small gradient expansion in T, in the center of mass.
Right. Right. So you claim that this center of mass coordinate change dependence on it is in some sense slow. And I don't want to go into details what means in some sense. Okay? Very good. So in particular, the important thing is that if you have a commutator of two operators, to zero approximation, if you just limit yourself to 1 in this expansion, then you say that Wigner transform of the product is a product of the Wigner transforms. Right? So that's a trivial statement. Now, if you think about commutator, and that's what we need to think here, right? Then this trivial part drops, because of course algebraic products commute and nothing left. So what is left out of the product is the first term in this expansion, right? And I wish I would know. So this product, in a sense of multiplication, will go simply to I dx d ta d epsilon b minus d epsilon a dt b. Now you see that if instead of epsilon and t, I will recall that I also have r and r prime here, r double prime and r prime, and do the same trick with respect to r, then I will have here also center of mass coordinate and momentum, relative momentum. Then this thing will be nothing else but Poisson greater. Right? If I combine time and space, this is essentially u obligatory. Okay? Good. So
Alex,
this.
can you write that out?
What?
How can you show that this is a Liouville operator, because I don't see it immediately?
We'll obtain it in a second. Okay, so now we want to understand what is this commutator. So let's do it sort of in a pedestrian way. So I have, and I want to go to the Wigner transform, right? So the Wigner transform of I dt is what do you think?
I dt.
Just dt.
Hmm?
This is dt. I dt.
No?
Just
Hmm? Think about what would it be if it's everything is just translation and invariant.
Psi omega.
It's just epsilon. Again, minus or plus, I have no idea, but it's just epsilon.
Because if you have convolution,
So this is epsilon, and this is some function which depends on t and epsilon. Right? And now I apply this, so I should say that this is whatever I, and then epsilon does not depend on t. So this term is not there, so the only term is there. So I have minus d epsilon of epsilon, and then dt of f of t and epsilon. Right? So surprise, surprise, what I get is I dt of f of t and epsilon. Pretty much what you could expect without any algebra whatsoever, right? But remember that here I still used to have t prime, point function. This manipulation is about to say that if I use instead a Wigner transform, then this commutator goes into this stuff. Now, slightly more tricky, let's think about this guy. So, grad square f. Now I'm playing with the same game with respect to spatial Fourier transformation. Right? So this guy goes into what? How do I call it? P? P. P square minus P square probably. Right? And this guy of course goes to f of R and P. Okay? And then again I apply this. There is no, if I try to take derivative of p with respect to r, this is nothing. So all what I get is I minus dp of p square, and then dr of f. Now notice that p square over 2m is nothing else but my dispersion relation. It can be anything. I mean, I just took p squared for as an example, it can be any dispersion relation. And what I'm doing, I'm saying dp of epsilon of p. What is it? Right, it's group.
Yeah.
Velocity. So what I'm getting is that, again, up to it's I, V, P, gr of f, r, p. You see, this time it's not quite that trivial as this time. Right? So you would think that it's just second derivative of f. It's not. It's this ballistic propagation of your excitation. Okay, very good. So yes, for this one, you of course also have. Okay, let me see what it is. Do I want to do? So V F will go to I dV d R dF dP, and then minus I call it, and then minus I dV dt dF dx. Okay. Now, forget for a second about time dependence of your trap. Let's be a little bit more simplistic. So what you see is that what I generate is dVdr is a classical force. That's what you would expect. And it comes with dF dP. It's a classical force translates you in p direction in a phase space. Okay? So notice that this F, which depends on R and P, it's a function of a phase space. Okay? And your operator is moving somehow this function in the phase space. Right? So the potential moves you in a p direction because p dot is equal to force. And yeah, so velocity is moving you in the r direction. Right? So you have velocity, x dot is velocity.
You can also think of that as acceleration, right? dVdr.
Yeah, that's of course acceleration.
Right. So then
And that is a
P
translation.
dot, sorry, but or P dot.
The velocity. Okay. So all in all, of this term what I'm getting is trying to make George give me. So I'm having something like I dt f, and then I have plus or minus using the notes. Okay, again, it's plus or minus, excuse me for the mistake, so it's Vp dr f, and then plus dv trap dr dpf. Now you can. So if you think for a sec that you have a Hamiltonian which looks like epsilon of p plus v trap r, then you immediately see that this thing is a Poisson breaker of your Hamiltonian and f. Hamiltonian f Poisson breaker. dH dP give you this, it comes with dr df, and then dH dr give you this, and it comes with df dP. So So what we got here is a left-hand side of the kinetic equation, or it's called kinetic term, if you wish. And the structure of this kinetic term is time derivative, time change of your distribution function, and the new V then was on bracket of your distribution function with a classical Hamiltonian.
And now if you didn't neglect this time-dependent term with potential, so what
Yes, if potential is time-dependent, it's a little bit more tricky. Nothing that much, but I have only 5 minutes and I have more important things to convey. Yes?
So this looks like Boltzmann equation.
It is a good.
And so Boltzmann equation is exact as long as you take care of collision integral.
Well,
or I can so-called exact.
Sort of exact, yes. So, so one thing is that you never know this thing exactly, right?
I mean, at least left-hand side is exact. It's
and again, left-hand side is exact, provided you committed yourself to this lower order expansion of the Maillard term. Right? So there is a scale separation behind it in space and in time. Right? One can discuss what are conditions for spatial space separation, temporal scale separation. There are assumptions, right? It's not an exact science in this sense.
It's the same assumption that goes into stat mech, right? When you close the equations at just one collision interval instead of going to 3 particle distributions, 4 particle distributions.
Well, to a zero approximation, yes, but there may be some related to the fact that your sort of potential may be big, but that doesn't necessarily mean that the scattering length is big. So there are some, but to zero approximation, yes, just standard statistics. All right, so this is the left-hand side. Now, in the remaining 10 minutes which I have in this class, I want to discuss the collision integral. Okay? So then again, so this is just sigma Keldysh, and I do my Wigner transformation. So this is a sigma Keldysh now in a Wigner transform sense, T epsilon R and T. Okay? These guys, they're slightly more complicated because they contain convolutions, right? And this convolution has zero order terms, just algebraic product of Wigner transform of sigma retarded times f minus f times Wigner transform of sigma advanced. But there are also commutators. And there are also terms like this. So what the commutators will do, and I'm saying it very briefly, it will generate df dr and df dp with derivative of complementary derivative of sigma r and sigma a. And they will renormalize your kinetic term. Essentially, you can say that real part of the self-energy of R, P, in principle, T and epsilon, renormalize your bare Hamiltonian. Okay, I'm doing it relatively sketchy, but just for you to know where it's coming from. It's coming from looking at this term and taking commutator term in the Wigner transformation. Okay? The real part comes from the fact that I always have retarded Wigner transform sigma minus advanced, and since it's Hermitian matrix, they're mutually Hermitian conjugated. What remains is a real part. Okay, so the real part of self-energy is, in a sense, renormalization of your both spectrum, and that's this dependence, but it's also renormalization of your potential, and that's this dependence, and it's also renormalization of your. time dependence that I cannot go into for now. All right? Now what remains, provided I already take care of the commutators, what remains is just algebraic products. Okay? And that's a collision integral. So now we know what are sigma k, sigma r, and sigma a for our simple example. So I want really to take one step forward and really see what is the collision integral for this simple example. Good. Yeah. Good.
Alex, you still have to demonstrate that one first term is in and the other one's out? Is that-
What?
You denoted the first term, the Keldysh part is in, and the other one...
Yeah, that's precisely what I'm sort of trying to do. Okay. Good. So my collision integral is sigma Keldysh minus, and now I'm just keeping algebraic manipulations, so I don't care about order of operations, so it's f sigma u target minus sigma u. Okay. Now what? Now I know what my components of self-energy are, right? And again, I use Wigner transforms of this of all these Green functions instead of matrix multiplication. It was not matrix multiplication to begin with; it was just algebraic multiplication. But now I substitute them by algebraic multiplication, Wigner transforms. And the last thing which I should remember is that with GK, which appear in each and every one of them, is nothing else but again f of f g the target minus g the box. So now look what happens. So let me first look at this now. So they both contain sigma Keldysh, and then they have G advanced minus G retard. This is, I'm doing it schematically, and then I will bring it back. G Keldysh, G retard minus G advanced. Okay? And now, if I recall what is G Keldysh, I'm getting F G retarded minus G advanced. They have different arguments. I'm just showing you the schematic structure. Now this one is entirely written here. So I have G Keldysh somehow. So that gives me F minus G advanced. G advanced minus G advanced. Then plus the same thing squared. So again, this comes from sigma Keldysh, and this comes from this.
I was saying this is already now a Wigner transform. So you
Yes, but everybody already did that transform.
That's why in the first line you were able to put F on the left side.
Say again, this one in the first line, but
in the first line and the second term on the right, F is on the left-hand side, as opposed to...
Yeah, I don't care about orders now, because it's now all algebraic multiplications, yes.
So you're taking the zeroth order term.
Again, there is a first order term, there is a commutator, which is sort of
right.
described, which went into here.
Okay.
But, and what is left is just three vectors in a sense. Okay. Good. Okay, so so now what do we got? We got kinetic term dt minus whatever h acting on f with some indices. Let me suppress probably spatial indices and keep on the time index. I don't know. Use p for both omega, epsilon, and k. So that will be relativistic notations. And it also depends on x, which I r and t. They always come together, so there's no much sense to distinguish between them. Now, this is equal to collision integral, which is a functional of this f. And in our simple example, we know what is this function. Also, let me try to sort of write it down. It's our interaction constant square, something else which I don't want to bother. Sum over intermediate four-dimensional momentum q. Then I have this thing g retarded minus g advanced, essentially of q, and g retarded minus g advanced p minus q. So this is the thing which typically is a matrix element square in your naive golden rule way of writing collision integral. Okay. It comes as this gr minus j's, and if you know them, if you solve your Dyson equation for gr minus j, you know what it is. But in general, it's it. But the most interesting part is what is remaining, and it's f of x and p minus q, f of x and q plus 1. This is this and this.